So here's the question. Number one here, are phone calls equally likely to occur any day of the week? So what do you think? So you understand the question we're trying to answer. Is it true that phone calls come in, the same number of phone calls come in to, you know, maybe to a cell phone Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, and Sunday? Is it the same? I mean, roughly about the same number of phone calls that come in on that? Is that roughly equal? Do you think you get the same number of phone calls? Do you think most people get the same number of phone calls roughly, approximately, about every day of the week, Monday through Sunday? Or do you think there's certain days when there's more phone calls?
Well, a certain day with more phone calls?
Yeah, what days would you think, Natalia?
Fridays.
Yeah, probably, huh? Probably weekend days, huh? Yeah, probably it's not the same. Probably there's more phone calling on the weekend. Maybe, I don't know. I mean, I guess if you're a business, there'd be more phone calling Monday through Friday. Yeah, but I definitely think there are differences, huh? Don't you guys? It doesn't seem like all the days are the same. We all know that certain days are different. The weekend days especially are very different from the weekday days. What we do is often very different on those days, and that'll probably affect the number of phone calls. So it seems like my guess would be that the number of phone calls are not equally likely, right? That's what we're trying to figure out. Equally likely. Is there going to be like an even spread of phone calls across the week? I don't think so. So that's what we're testing. How do you test something like that? This question, do you realize, is a goodness of fit question. Meaning, we're wondering, does it fit with the, and what are we wanting to fit with? Does it fit? Does real life data fit equal number of calls every day? That's really the question we're trying to answer here. Does that make sense? Does real life data fit equal the idea that, hey, you probably get the same number of calls every day? I don't think that's true. I think the days are not the same, and real life data will show that. Even look at the real life data we have right here. So here's what they collected some data. So they did some kind of statistical experiment. They took somebody's phone or a business's phone or a, I don't know, because that's I don't get 91 calls any day, and so I don't know. Well, they took maybe a whole group of people. Maybe they took like 50 people. And they said, all right, tell us, each of you report how many calls you got, for a whole week. And 50 people maybe reported, and they did a big study. And they took a bunch of people, and they said, all right, tell us. On Sunday, everybody all together got 91 calls. On Monday, 68, Tuesday, 71, etc. It just glancing at the data, does it seem like the real life data, does real life data fit with the idea, fit with, it's a funny looking with there, fit with equal number of calls every day? I don't think so. Do you? Looks like they got more on Sunday. Like a lot more. I mean, of course, none of them are exactly the same, but see, like these four are very similar, aren't they? So those four seem like they're about the same. 68, 71, 69, 62. Those are pretty close. Maybe Tuesday's a little low. But in general, those are pretty darn close. So those days, Monday through Thursday, seem like they have the same number of calls. So if they had just asked us, do you get the same number of calls Monday through Thursday? I think real life data would support that. Does fit with that? This is goodness of fit. Does real life data fit with equal number of calls every day? I don't think every day. Monday through Thursday, yes. But Sunday looks very different. Friday and Saturday, certainly very different, huh? So I think the answer is going to be no. But what we want to do is have our calculator calculate what it is. It's the p-value, which is the probability that these differences are just luck. Because that's always the question, right? Whenever you study something, you're always, you know, I could write the question here. Are the days all equal or the same? Same number of calls. Are the days, do the days all have the same number? No, definitely not, right? 91, 68, 103, no. They are different. So, I mean, it's a simple question. Just look at them. No, they're different. They're not all the same. Of course. Boy, this was easy. Let's go to the next question. Answer is no. Done. Well, it's not quite that simple, is it? Why not? Why is it not that simple? Well, because of luck. Maybe these differences are only, well, here, yeah. Let me say it a little bit better. Let me say it better than I'm saying it. Here's the problem. I want you to get the big idea, because that's what's most important. You're probably never going to do an actual statistics test after this class is over, which you might be thankful for. I don't know. But you'll read data studies and understanding them. You'll hear people give data and evidence, and understanding is what's most important. So maybe here's the issue. Why can't we just say no? Look at them. They're not the same. Well, maybe all the days really typically get the same number of calls, and these differences are because of random luck. Right? What about that? What if somebody said, yeah, you know, like think with me, guys and gals, for a minute. What if I was to take a coin? If I was to flip a coin, what's the chance I would get heads? Remember back in our probability section?
It's 50%.
Yeah, 50-50, 1 out of 2, huh? Exactly. So if you flip a coin, the probability of heads is 1 out of 2, or 50%, however you want to say that, 0.50, right, totally. Okay, so what does that mean then? If I flip 2 times, will I for sure get, you know, or how about if I flip 10 times? If I flip 10 times, will I for sure get 5 heads and 5 tails? Is that what happened?
No, the 50% is an average over time.
Yeah. The fact is you could get lucky and you could get maybe, you know, 6 heads and 4 tails because of just random luck, right? And we would never look at that and go, oh, see that coin, that coin gives heads 60% of the time. It's not really 50-50. Nobody would say that, would they? They would go, that's ridiculous. It's just random luck. It just happened to get 1 more head than tail, right? And what if you flipped it and got 7 heads and 3 tails? Same thing. People go, oh, well, you just got lucky. I mean, it's really 50-50. You just got lucky. What if you got like 2 heads and 8 tails? Well, you just got unlucky. And that happens every now and then, but really it's 50-50, right? That's what everybody knows to be true. Well, that's exactly what we're wondering about over here. Maybe really all the days, you know, typically come out the same number of phone calls, and we just happen to get a lucky a lucky sample, you know, by random luck, where they kind of came out different. Like this is 103 and that's 91. This is only 7. Maybe that's just because of random luck. Maybe all the days are really typically the same, like the flipping the coin kind of thing. And these differences are just because of random luck. Or maybe not. What if I told you, hey guys, what if I was to flip a coin 100 times? How many heads should I get typically?
50.
50, right? You should get 50 heads and 50 tails. But of course, that's not going to exactly happen, is it? You know, I might get like, if I got 53 heads and 47 tails, you wouldn't be shocked, would you? You'd go, oh yeah, well, that just happens. That's just, you know, it's about 50. So it's just a little bit of random luck. But let me ask you this, guys. What if I got 100 heads in a row and no tails?
That seems unlikely.
Yeah, you'd start to wonder if I had a cheaty coin, if my coin really had 2 heads, right? This is, in fact, I wish we were face to face now. This is my favorite thing I do in class. I actually come to class with a 2-headed coin. This is my typical, this is one of my favorite days in class. And it's a lot of fun because what I do is I go outside the classroom and I always grab one of the first students coming down the hall who gets to class first. And I ask him or her to, I hand them my coin. Seems like it's always been a her. I hand her my coin and I'll say, hey, would you be willing? I'm going to ask people in lecture if anybody's got a coin that I can flip. I would like you to volunteer this coin. I'm kind of tricky. And the gal is always like, oh, sure, Mr. Heron. So then we go to class and I start lecture, and about 10 minutes in I go, hey, let me show you with coin flips. I go, does anybody have a coin? You know, a bunch of people raise their hand. And of course, I take the gal who's got my coin because I'm trying to fool everybody. I'm like a magician trying to do a trick. So anyway, I grab the coin and I start flipping it. It's got 2 heads on it. It's a trick coin I ordered off the internet a couple years ago. It's got 2 heads, but I don't show anybody, you know, and nobody suspects it at first because I just got this coin from this gal, supposedly, right? So nobody's expecting anything. So I go, what's the chance if I flip, you know, 10? So I start flipping and it's like heads, heads, heads. And I show them, you know, I flip it and I let it land on the ground so everybody can see that I'm not just saying that. I don't let them pick up the coin and look at both sides, but I'll flip it and I'll let them see it land. I'll show people, I'll go around the room and I'll show people that it came up heads, you know. And after 3 heads in a row, I go, wow, I'm lucky. And everybody's like, yeah, you're lucky, Mr. Heron. And I get 4 heads in a row, 5, 6, 7, 8 heads, 9 heads in a row. And pretty soon everybody's like, Mr. Heron, what's up with that coin? Or they'll act like, usually they think that I'm just like some tricky flipper, that I've got some sleight of hand, my wrist is tricky or something. That's not the case. And so I'll have one of them flip it. I don't let them look at both sides, but I'll hand them the coin. I'll say, you flip it then. They'll flip it. It's heads. Somebody else want to flip it. Somebody else flip. They flip its heads. I'm like, guys, we've got like 12 heads in a row. Do you really think this could happen by random luck? And I'll start taking a survey. And some people still think, yeah, maybe you're just getting lucky. I'll go, okay, let's flip on. And, you know, until we get like 15 heads in a row. And then I'll say, how many people think we're just getting lucky? Pretty soon, nobody thinks that anymore. No hands go up. And everybody is convinced that there's something funny with the coin. And then I show them, yes, you're right. Of course you're right. It's a 2-headed coin. This can't happen by luck. Okay, so my point in that example, so hopefully you can feel that example that I described to you. What I want people to feel is exactly what we're doing in this section, really in every hypothesis test in statistics, is we're wondering, could this thing happen by random luck? And if it gets super unlikely, if you get 100 heads in a row, there's just no way that's going to happen. You know what the odds of that are? It's like winning the lottery 10 times in a row, right? You know how the lottery goes, right? Think with me for a second. If you won the lottery all of a sudden, everybody would think, wow, you're lucky. If you won it again the next week, people would be shocked. And they would go, you are crazy lucky. And then if you won it again the 3rd week in a row, the police would come to your door, wouldn't they? And you'd be talking to the FBI and all those kind of people because they wouldn't believe it's luck anymore, right? If you won the lottery 3 times in a row, you would be under arrest or at least investigation for what's going on. Right? So we all sense this in society, that there's luck and that there's stuff that's just beyond luck. That's just no. Nobody's that lucky. Something's going on. They're doing something. Well, that's the basis of all that we're doing in statistics. I hope that idea is coming across. That's what we're doing in all of our hypothesis tests. We're saying, is evidence strong? In other words, is it beyond a reasonable doubt? Just like in a court of law. That's what you do when you have a convicted person, somebody accused in a court of law. You listen to the evidence that the prosecutor puts forward, the district attorney, and you try as a jury. I've been on a jury a couple times doing this. You try to decide, you try to weigh the evidence and decide, is that evidence really strong so that it's beyond a reasonable doubt? Meaning, you can always try to say it was luck. Maybe it was just luck. The person was in the area when the murder happened. Maybe it's just luck that their glove was found, around the murder scene. Maybe they just dropped their glove down the alley. They were there that day. But then all of a sudden, when you've got their blood or the victim's blood on them, at this, some of the, if there's enough evidence like that, you start going, no, you don't get, the person's blood wouldn't be there by random luck. That can't happen. No way. That's strong evidence. This person did it, and you convict, right? Because the evidence is beyond a reasonable doubt. Well, that's exactly what we're looking at. And that's what we're doing today with this goodness of fit. When we look at these numbers and we say, well, maybe they're really all the same typically, and they just came out a little different this time because of random luck. Maybe we just got a sample that's a little weird. And if you got 53 heads, you would think, yeah, that's just random luck. But if you got 100 heads, you're like, no way. There's something up with that coin. So, and what tells you that? What tells you that is probability. The probability of getting 100 heads in a row is so low. You feel it, don't you? You don't know the number. I don't know the number either. But we all feel it's like impossible. The probability is so stinking low that there's no way that happened by random luck, right? That's why we say when the P is low, HO must go away, right? We want a low p-value. Remember what p-value is? P-value is the probability of luck. That's what it is. And if the chance of luck is super low, like the chance of getting 100 heads in a row, if it's super low, you're like, no way that happened by luck. But if you've got 53 heads only, that's not impossible. That could definitely happen. That doesn't have a low probability. We all sense it. I don't know what it is. You don't know what it is off the top of our head, but we all sense that it's not a big deal to get 53 heads out of 100. That could certainly happen. The probability of that is not crazy low. Just like the police know somebody could win the lottery once, maybe twice in a row, but if they win it 3 times in a row, they're cheating and they're under arrest, right? Because we all sense the probability of that is crazy low, beyond a reasonable doubt. So that's what we're always doing in statistics. That's what we're doing today as we look at these numbers. We're asking ourselves, are these numbers so wildly different that there's just not a reasonable chance that could have happened by luck? They must really be different, meaning typically different. They must, because that's the question. Are the days typically the same? That's what we're wondering. Are they typically the same? And they certainly came out different and even kind of strongly different. Like these two numbers right here. That's almost double, right? That doesn't seem likely to have happened by luck. But what our calculator will calculate for us is exactly what the probability is that could have happened by luck. That's called the p-value. That's why we're obsessed with p-value, because it tells us the probability that you would get whatever results you're looking at, whether it be a chapter 10 two sample test, or now in chapter 11 goodness of fit, proportions, means, whatever. The p-value is the probability that this would happen by just luck. And if that's really low, if the chance of being that lucky is super low, then you don't believe it was luck anymore. You start thinking, no, there's something going on there. Those are really typically different. That coin's a trick coin. Those days do not have the same number of calls typically. They really don't. You couldn't get that different by just luck. That's what we're looking at. All right. So I hope that makes sense. That's what we're testing. So let's dive in. What are we gonna do? Let's go to our calculator to find out exactly what buttons we're gonna push and what test we're gonna set up. So if go to our notes is what I meant to say. So I'm gonna go to the notes with you now, and the exam 4 notes, right? We're on the exam 4 material. So here it is, the exam 4 notes, you're seeing it. And we're looking for goodness of fit. So come on down. Yeah, there it is. Wait, I don't know why I put it way down there, but there it is on number 9. So way down to number 9, goodness of fit. Let me bring it over here for you all where we can write on it. So I hope you have the exam 4 notes either printed out or open in a window on your computer. You want to have it before your eyes because it's really important that we can see it. So have it printed or open. You're going to need to have it printed eventually to take the actual exam. So might as well print it right away for yourself and use it all next couple of weeks. All right, here it is. Number 9, goodness of fit test. How do we do it? HO is the observed and expected data fit each other well. So this is kind of nice. HO is always the same. The observed and expected data fit each other well. H1, they do not fit. And then you put the observed values in L1 in your calculator. You calculate the expected values and put them in L2. And if it says equal frequency, it's the total number of values divided by the number of categories. If they give you category percentages, it's each category percent multiplied by the total number of values. I'll explain that as we go. And then, depending on whether you have a TI-84 or a TI-83, if you have an 84, you need to do this. If you have an 83, you're going to use that program that I sent the link for. And do that little test, which is actually easier. The 83, once you have the program, you'll have an easier go of it, just like that. So that's the plan. So let's go back and start doing that. So on this one, we kind of erase all my maybe it's luck and these numbers are different and all that. So whoops, I don't want to erase that part. Yeah, maybe I better. All right, so we have room to write everything. Okay, are the days really all the same? Does the data fit? Okay, so what is the correct statistical test to use? What does it say about that? What is the correct statistical test to use? What are the options there on your computer in the homework?
Can you repeat that?
So what are the options it gives right here on B?
It says homogeneity.
Homogeneity? Yeah.
Yeah. Paired G test, good to fit, and independence.
All right. Yes. Okay. So we're doing goodness of fit on this one. Yeah. Let me try to get that up where I can see it too. Yes. Right. And so, yeah, our answer is goodness of fit. So right there, you're going to choose goodness of fit. Those other tests we're going to do next time. So goodness of fit, we choose right there. And then HO, what's HO going to be? It's going to be, let's read through them. Remember what it said down here, told us HO, right? On our notes, right here. HO is the observed and expected data fit each other well. Right? Does everybody see that? So the distribution of phone calls, that's not what I want, is uniform. So that's the one we want right here. Is uniform. Do you understand? That means uniform means they're all the same typically.
So, Mr. Heron, that is essentially the claim, right, of the question?
I wonder, is it what they could say either way? Yeah, good question. I hear your question, Natalia. Let me encourage you about this. We don't need to worry a lot about the claim in these problems because the HO is always the same no matter what, which is nice. It makes it kind of easy. HO is always that they fit. Now you're right that they could claim this one or they could claim that one. Like somebody could say, I think they fit, or somebody will say, I think they don't fit, you know? So they can say it either way. But for our purposes, what's nice is we don't have to worry about it a lot. It's always going to be HO is that they fit and H1 is they do not fit. So yeah, do they actually make a claim somewhere? Or do they just ask the question, are the phone calls equally alike? Yeah, so I guess that's kind of the claim. So yeah, you're right. You're right, Natalia. That's correct. That's their claim or their question, I guess it is. Are the phone calls equally likely? Are they kind of like the coin, right? Is this a fair coin? Is it a coin that typically gives half heads, half tails? That's the kind of question. If I flipped 100 heads in a row before you, you would start thinking, no way, that's a fair coin. So that's what we're at. They're claiming that the days of the week typically have the same number of phone calls. So that is the claim. Yeah. So I'll just put a box right there. That's the claim. And then the HO, as I said, is the distribution of phone calls is uniform, meaning all the same typically, just like a coin typically gives the same number of heads and tails, right? It's uniform, typically. Not always though, but typically, right? And then H1. What's H1?
So I have a question, Mr. Heron.
Yeah, Juan.
So what is typically uniform in this question before I can see it?
Something is
it like the days of the week
all,
because the numbers don't add up? What's uniformed here?
So uniform would mean that they're typically all the same.
Well, I know that, but what are we looking at to get that hypothesis that they're uniform? What shows us that they're all equally besides the claim itself?
Yeah, it turns out well, we're going to test that claim based on these numbers. So let me make an analogy. What if I said to you guys, hey, I have a coin. It's a fair coin, I said, and I flipped it 100 times. And to answer your question, let me go back. And it came out 63 heads and 37 tails. So that would make it seem a little bit unlikely that my coin is really typically a fair coin. And especially if I got like 90 heads and 10 tails, you'd be like, no way, Mr. Heron, is that really why? Because those are not very uniform, to put it lightly. Those are extremely not the same. So that's what we're doing. It's a good question. That's exactly what we're doing here. We're looking at these numbers and going, are they wildly different or are they just a little different? Because if they're just a little different, we could say, yeah, that could happen by luck. Just like if I flipped the coins and got, 53 heads and 47 tails, nobody would be amazed. Everybody go, yeah, that happens. I'm sure it's a fair coin. It's just by luck got a couple more heads than tails. That happens. But if I got 90 and 10, everybody would be like, no way. That coin is weighted too much on one side. Or if I got all 100 heads and no tails, nobody would believe it's a fair coin, right? So that's what we're doing. So to answer your question, Juan, and other people out there, I'm sure it's a good question. It's all about how wildly or unwildly different these numbers are. And the calculator is going to tell us that. We're going to put them all into the calculator, and the calculator will give us the chances, the probability, the p-value that this could happen by luck. That's how we're going to test this. All right. So it's just like the coin thing. Just keep thinking about the coin thing, right? You'd expect a coin to come out the same number of heads and tails. And if they came out really different, you would start to doubt whether that's really a fair coin. So that's the null hypothesis. Write that here. The distribution of phone calls is typically uniform over the days of the week. That's the null hypothesis. Okay, and then the alternative hypothesis. What's the alternative hypothesis going to be on this one? Well, it's going to be the opposite of that, right?
Yeah, not equal to.
Yeah, so we said uniform. So what's the opposite of uniform? Right there, not uniform. Right, y'all seeing the different options on the H1? The distribution of phone calls is not uniform. That's the opposite of uniform. So uniform means they're all the same. Not uniform means not typically all the same. Not typically all the same. Like a coin that I flipped and got 100 heads in a row. Nobody would believe that's a fair coin that typically gives 50-50 and I'm just really lucky. Nobody would believe that. That is the alternative hypothesis. So that's always the strong evidence, huh? It's going to take us strong evidence to be convinced that that's not a fair coin, that really the days of the week do not have the same number of calls. And up here, this only, if evidence is weak, then we're going to end up going with HO like always, right? HO is always our conclusion with weak evidence. Just like in a court of law, you assume the accused is innocent. And if the evidence is weak, you stick with the innocent. There's nothing going on here. But if evidence is strong, beyond a reasonable doubt, really low chance of luck, low p-value, then you say, no, there's no way that's luck. That person did it, and you convict them. All right. That's exactly what we're doing in a hypothesis test. All right, let's come on down to part D, degree.
So, Mr. Heron, the C section is just like what we've been doing, but it's just laid out differently in words, right?
Yeah, it's just another hypothesis test. All of these.
It's a different form, basically. Okay, thank you.
Yep, degrees of freedom. So now, did I put on the notes degrees of freedom? I don't think I did. I think I forgot to put that on your thing. So let me see. So, well, I'll just tell you right now, and I'll add it to the notes later. I guess would be the best way to go. It's always that. I didn't put it anywhere, did it? Oh no, there it is. Right there it is. I didn't see it. Yeah, right over there. Degrees of freedom, DF. I just abbreviated it because I was running out of room in that line. Degrees of freedom, right there, DF. It's number of categories minus 1. So the degrees of freedom is the number of categories minus 1. So we come back here and we go, okay, so what are the number of categories? How many different categories do we have here? 1, 2, 3, 4, 5, 6, 7. 7 days of the week. That makes sense. So degrees of freedom is going to be 7 minus 1, 6. Good there? So number of categories, here, I'll write that out. Number of categories minus 1. It's something your calculator needs to know when you type in stuff. No, degrees of freedom, so it's going to be 7 minus 1, it's 6. 6 different degrees of freedom, they call it. I won't bore you with the details about what that's all about. The calculator's gonna, for the people with the TI-84 anyway, calculator's gonna ask you to put that in. All right, let's do the next one, the test statistic for this data. So it's time to go to our calculator. How are we gonna do it? Well, let me look down here at the notes again, and I will show you. So what does it say? it says, put the observed values in L1. Let's do that first. So come back up here. That means, get rid of this coin flipping stuff. That means that I'm going to take these numbers and put them in L1 in the calculator. So that's the first thing you do. So let me go over here and go step number 1. Put the numbers down L1. You know how to do that, right? Clear out L1, you know, you go to stat and you're already on the edit menu. You just hit enter. You go to the top of L1, you hit clear and enter. And you might as well clear out L2 right now too, because we're gonna use L2 in a second. Go to the top of L2, hit clear and enter. So clear out L1 and L2, and then put the numbers down L1. All right, so once you got those numbers down L1, then we're gonna have to get numbers down L2. How are we gonna do that? That's the part that's more tricky. You're gonna calculate the expected values and put those in L2. What do we mean? If it says equal frequency, which is our case, that we're expecting all the numbers to be equal, right? On the days of the week, that's the claim. The days of the week have equal likelihood. What do? Take the total number of values and you divide by the number of categories. Everybody seeing that little formula? And that's what's going to go in L2. All right, so let's go up here. Let me show you what they're saying more clearly. They are saying, all right, so step 2. And see how it says expected up here? Expected. L2 equals the expected column. And what does it equal? Total number of calls divided by number of categories. So what's the total number of calls? I don't know. We're going to have to, oh, they gave it to us right up here. 553. Right, so if you added all these up, they're saying you're going to get 553. It's nice. We don't have to add them up on our calculator. They just gave us the number right there. So there's a total of 553 calls. That's the total number of calls. 553 divided by what's the number of categories? 7, right? So in other words, what we're saying is we're saying each of these expected frequencies is equal, right? And what is that? That comes out, if you divide that on your calculator, it comes out to be 79, doesn't it? So we're going to put 79 for all of these.
And that goes all the way down L2?
Exactly, all the way down L2. And that is L2. Exactly right. You put that all the way down, which I'll show in just a second. That's right. That's right. Now I want you to see why. Because I don't want this just to be some mysterious thing, because that's no good for you, right? The whole point is that you understand. Because again, real life, you're probably never going to do this again in 3 weeks when this class is over, but you will hear the results of other people doing data analysis like this. I want you to understand the meaning. Why are these the same?
So our numbers are 1, 5, and 6.
Because wouldn't that be the mean
Okay, Ava B.
every single day? That
Yeah,
should be the
right.
average.
Exactly, Natalia. You got it. Good. I'm glad you're dialing in with it. Right, that's the average. In other words, if they really were the same number of phone calls every day, that's the numbers we would expect. That's why they call it expected, right? That'd be like when I said I expect to get 50 heads and 50 tails, right? If the coin is really fair, I would expect to get 50-50. Right? I would expect to get the same number. Now, we know it's not going to come out perfect 50-50, but that's in general what I would expect. Well, that's what we're doing with the phone calls. We just said, well, if they're all really the same, if you really get the same number of phone calls, like the claim, right? The claim up here, equally likely, same number any day of the week. Well, if that's the case, then the total number of calls, 553, divided by 7, that's 79 calls a day. every day should have the same number of calls, 79 calls. That's what we would expect if really the days were equally likely, like the coin, same chance of heads and tails, right? So put those down L2, which I'm going to show in just a second. And
When Mr. Harry,
do the test, which is right here. Question.
yeah, I got a percentage.
I think you probably put this upside down. The bigger number
No,
come first?
I put it, yeah, I put the higher number first, and it
What
gave
number
me
did you put?
7.56.
You got what's that?
I got 7.56.
Did it stop right there or did it go on and on?
No, it just stopped right there.
Yeah, no, that's totally fine. You can get a decimal. Yeah, if you got 7.56, that's totally good. Just put 7.56 all the way down the line. Yeah, it's totally fine to get a decimal. That's good. Yeah, and if you got it decimals that go on for a long place, really you should probably, you know what you can do also, if you guys want, you can just type in the fraction every time, because that's a little more work, isn't it? You can just type in the 553 over 7 every time down L2. All right, I'm gonna show that now. And so you can see that on my screen as well. Let me go there. All right, you're all seeing my calculator on my screen. So I'm going to go to, oops, that's not what I meant to do. There we go. Okay. Move this over, there we go. All right, so you're all seeing it front and center. It's just a little bit over. Okay, so here we go. So I'm going to go to, what are you going to do first? I'm going to go to Stat. I'm on the Edit menu, hit Enter. My L1 and L2 are already clear. So if yours are not, you know how to do it, right? You go up to the top there, press Clear and Enter. And that'll clear it out. Go over to the top of L2, press Clear and Enter. Okay, they're both clear. Then down L1, I'm going to put the numbers that I had. 91, my numbers. Okay, and then go over to L2. And now, like I said, in L2, if you want, you can just type the fraction every time. Watch, 553 divided by 7. Enter. And see, it'll make it 79 for you. And so you can just do that. If you've got a really long decimal and you don't want to type it in, just do the fraction every time. 553 divided by 7. That'll be fine. If you got a nice whole number like 79, it'd be quicker just to do 79. But if you got a long decimal, just retype the fraction that you divided every time, and the calculator will calculate it for you. Let it do the hard work. All right, there we go. So I've got my 79s down my L2 all the way, got my L1s in there. All right, now what am I going to do? Well, according to the notes, I'm going to go Stat. Now this is for the TI-84. I have an 84. I'm going to show you both ways though. Oh, no, wait, I can't show you the other way because I don't have it on this calculator. Yeah, sorry. I'm just going to show you the 84 way. Go over to tests and go down, 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 down. There it is. Chi squared. That's a Greek letter called chi. Anyway, it looks like an x squared right there. The x squared, which is really chi squared, GOF test, goodness of fit. There it is, the goodness of fit test. It's D. It's way down on D for the TI-84. Now, the TI-83 people don't have it. For the TI-83 people, you do not have this program. It's not built into your calculator. I'm sorry, TI-83 people. That's why you need to program the one I sent you, the link I sent you, and yours will be nice and easy. So I'm going to click Enter. Let me show this one first. And then I'll refer to the notes for how you do the TI-83. Click that one. It says, okay, observed data, yeah, L1. That's where we put the observed numbers. like the data we saw, what did happen Monday through Sunday on the phone calls. The expected, that's what we thought would happen if they were really all equally likely. That's down L2. That's 79 for me, all the way down L2. Yeah, we're just telling the calculator where to go find the observed values and where to go find the expected values. Now, degrees of freedom. What was that? That was supposed to be 6, wasn't it? Remember, because it was number of categories minus 1. 7 days of the week, 7 categories minus 1, 6. Go down to calculate and hit enter. And you know what we care about? The p-value.
Mr. Heron, I'm sorry, I didn't get that very first part. What did you put in to calculate all this stuff?
So
What test is that?
I went stat, tests, and way down to D, goodness of fit test, GOF test.
Okay, thank you.
Yeah, for the TI-84. So that's for the TI-84. Go down test, all the way down to GOF test, goodness of fit test. Hit enter. And then you want L1, L2, degrees of freedom 6, because that's 7 categories, 7 days of the week minus 1. And hit calculate. So there's my p-value, which is the probability that this is just happening by luck. That looks pretty darn low, doesn't it? The chance that these days of the week are really all the same and we're just getting these differences by luck is pretty darn low. That's like me saying, yeah, this coin is really fair. I just got lucky and got 100 heads in a row. No, the chance of that is super, super low. We don't believe it's luck. We believe there's something going on with the coin. It's not really a coin that gives equal numbers. So let's go back now to my iPad. All right, so we did all that information. Oh, and let me refer you to the notes again here. So if you have a TI-84, like I just showed here, stat, test, the X squared or chi-squared, goodness of fit test, observed is L1, expected is L2, degrees of freedom is number of categories minus 1, so that was 6. Now, if you have the TI-83, you have to use the you have to hit the program button, which is right in the middle. PRGM, this button is in the, it's in the middle of the keyboard, just under stat, right? It's just under the stat button. Yeah, that'll be easy for you to find because you're always using the stat button. So it's just under the stat button. You have to hit the program, which means go get one of the programs, choose this program and hit enter. And it'll just do it automatically. You won't have to put in any other information. It'll just do it automatically for you. It's very nice. Once you put that program in your calculator, which I'll help make sure everybody gets it into their calculator today. So either way, you'll get your data. Oh, and it tells they want the test statistic. I forgot to get the test statistic. I didn't know they wanted that. Let me go back. And I gotta waste some time here. Sorry. All right, there it is. That's the X squared thing, which is really chi squared. It's a Greek letter. It's 17.64556962. That's the test statistic, and underneath it is the p-value. So, all right, let's go back to the iPad. Got to link this up again. Sorry, that wastes a little bit of time there. There we go. Okay, so back to it. The test statistic, they wanted 3 decimal places. So mine was 17.646. I think I need to round 6455. So 646. And then it says the p-value. They always want those to 4 places. So 0.007. I got 1/8, so 2. 0072. The question is the p-value, same thing we're always doing. The p-value, which is 0.0072, the alpha, we're always testing compared to the alpha level. Where was the alpha level? There it is. Significance level, way back in the mean. That's your alpha, right? In other words, that's how strong they want the evidence. Are those alpha levels and p-values starting to make more sense now, right? The p-value is the probability of luck. as I keep saying. And the alpha level is how low you want that chance of luck, right? It depends, and which that depends on how serious the test is. If you're testing a new treatment for cancer or COVID, right now they're trying to find a vaccine for COVID. You want to know that the chance that that luck got in there is super low. You don't want some random lucky thing to mess you up when you're going to give a vaccine for COVID to the whole nation, right? You don't want that. You want to know that there is virtually no chance of luck, right? So you would want a really, really low alpha level. The lower the alpha level, the lower the chance you're going to let luck get in there. You're saying, I want under a 10% chance of luck before I'm going to believe the evidence is true. That's what you're saying. That's what the alpha level is. It's how low you want the chance of luck to be. You want the chance of luck to be lower than 10% if you're going to believe the evidence. So the alpha level, they said, is 0.10. So did our p-value come under the alpha level on mine? It did, huh? It's less than. So the p is low. So the HO must go away. You know the saying, right? If the p is low, the null must go. So the p is low in this case. So the null must go away in our case. So coming on down, what is our case? So based on this, we should, and the answer here would be reject the null. For me, at least, because I got a low p. So the null must go away, right? We're going to reject the null, right? Reject the null. Everybody good there? When the p is low, the null must go away. You must reject the null. So what does that mean? That means let's come back up here. Look at the null. Here's the null. We're saying no way to you. We're rejecting that, and we're keeping the other one, right? We're always going to go with one of these two attorneys. So we're keeping the other. What does he say? The distribution of phone calls is not uniform. That's what we keep and believe. In fact, there's strong evidence. There's strong evidence in this case that the days are not all the same, right? Which we saw, right? These days did not come out all the same. And not only by a little bit, 103 is almost twice as big as 62. They came out wildly different. We do not believe that that's a fair coin. That's like flipping a coin and getting like 80 heads, 90 heads. No way you're going to get that by luck. The chance of luck is super low. We believe that's an unfair coin. It's weighted to one side unequally. That's what we believe about these days. There's no way that they're going to come out that different, almost double, by just random luck. They're not really typically all the same. They're different. The days are different. That's what the evidence says. We keep the strong evidence that the distribution is not uniform. The days are not the same. This is strong evidence that the days are not the same. You know, strong evidence, that's the same as sufficient, right? Sufficient means enough. I don't know if everybody knows that word. Sufficient means enough. You know, if you say, I had sufficient dinner last night, I had enough dinner. I guess we don't ever use that word with dinner, but you know, you know, sufficient means enough. So if the evidence is sufficient, it's enough. The evidence is strong enough to convince us that those days are not uniform. So let's go down and draw our final conclusion. So there is sufficient. Yeah, that means the same as strong, doesn't it? There is, so it's one of those two. It's not these guys. Oh, there's another one. Yeah, it's one of the, because sufficient means strong, means enough. So there's strong evidence. Okay, which one? Let's see. To conclude that the distribution is uniform? No. We said not uniform, right? Remember who we went with? We keep this guy that says not uniform. So that's not right. Let's try again. Not uniform. Yeah, that looks good. Dependent? No, that's not it. So it's this one right here. Right? Strong evidence, sufficient evidence, not uniform. The days of the week are not uniform. So that is our conclusion to that problem.